Hello everyone again. My name is Bryan with Spenties, and I'm joined by Sagar Shetty with Bionic Prosthetics and Orthotics. And today our webinar is meant to be extremely technical. Now we'll explain the acronyms in the beginning, but this is the type of webinar where it's just full of acronyms towards the end. So I hope that you learn a little bit about the scanning process. More about modeling, and before modeling, rectifying scans. And then we're going to get into detail about printers, printing materials, post-processing, and this is meant to be your jump start to 3D technology. And I hope that if you have any questions whatsoever, please put them in the chat. We will answer those questions at a later time, but what's really important here is that you're going to get the foundation for the scan, model, print flow that's now available in 2022. There's going to be references to Spenties, which I'm very excited to share with you all. There's going to be references to other companies too. So this isn't a commercial for Spenties. This is meant for you to take a deep dive into 3D technology in only 30 minutes. And I'm just so excited. So last week we talked about bionic prosthetics and orthotics digital workflow and how over time it's evolved to this scan, model, print flow. And you know, let's just jump right into it.
Sure.
Let's first start, we'll start talking about the most important aspect of the digital workflow, arguably, scanning. We have the phone/app. We have iPad and the structure scanner,
Right.
and then really the handheld white light, the very top of the line scanners.
Sure.
What's your experience with three of those scanners?
So we have used all three methods of scanning, and they all have its place. Obviously, the one that works with your phone or with just an app is the most convenient because you know, if you're a clinician that's very busy, and especially if you're a clinician that's seeing patients at different facilities all the time, you don't have to carry something with you. You know, you can just pull your phone out of your pocket and start scanning. So that certainly is something that practitioners would appreciate, and that technology has come a long way from where it was. And that's relatively new, being able to get a good 3D scan from just a handheld device, a phone. There are a couple different softwares available. Comb app is something that we have seen and used, and it works really well. It uses the front-facing camera to capture the scan, and we had pretty impressive results with that app. There are also other technologies, like Ortho America uses their own app to capture scans for cranial remolding technologies, which is FDA approved, which is also very, very convenient, especially when you're working with kids that are constantly moving.
Is that also the front-facing camera?
That is not a front-facing camera, actually, and but it's a different technology. You have to use a very specific sock on the patient's skull, or it also allows you to take a BK scan. But there's a very specific sock. It's a very unique technology that they use. Very impressive. But it works on an app on your phone. So that's one technology. It's very impressive. I don't think I need to mention that the resolution is not necessarily an issue with that, because if there is one type of O&P device that really requires a precise scan, that is cranial remolding, and the fact that FDA has approved an app that works on a phone, to be able to capture that level of accuracy is tells you something about the resolution that you can obtain with scans like that.
Yeah.
I believe Comb also has some data available on the resolution that you can get.
I want to expand on that. So I have a background in Apple technology and iPhones and things like that, and I was around when the iPhone actually released the Face ID. And you have to think of, and not think of, but the reality of the iPhone scanners is that they're using the same sensor that you use to unlock your iPhone with. When I was really into, it was the iPhone 10, I learned that there was actually 1 million sensors that are mapped onto your face to be able to consistently unlock your iPhone with only your face. So they have really dialed in the process, the hardware, the iPhone, to enhance security. But what I found just amazing is that folks have used that sensor to be able to shape capture people's residual limbs, their heads, their arms, to do that, and it'd be a critical piece of a much broader application than just for phone locking.
Correct.
That's really cool. So that's called the True Depth sensor, and it's available on any of the iPhones that have the Face ID.
Right.
So little nerd bit there.
Yeah. So I think that is the latest, the coolest thing out there in terms of scanning technology that's available right now. Because really, for a practitioner, it's about one, efficiency, and practically can I use this on a day-to-day basis. O&P is a very unique practice. It's not a practice where you are always just sitting at a clinic and patients are just coming into the rooms. In a typical O&P practice, you are seeing patients at your clinic, you're seeing patients in the hospital, you're seeing patients at a nursing home, you're seeing patients at so many different places, and you're constantly traveling to see all these patients. And if you have to always carry all your equipment with you, sometimes that can be a lot. So really having that access to making it easier to take a scan makes a difference.
Yeah, mobile applications do
Correct.
seem to be the future of
Absolutely.
of the digital workflow, and that points us to the structure scanner. It's been around probably as long as any other scanner in O&P, and I think that changed the game because that was the big step from the big cumbersome scanners to now an iPad-based scanner.
Correct.
Something that you can hold in your hands and it's easy to use. Some folks have had some trouble with dimensional repeatability. Maybe in the beginning when there were some of the earlier models of the iPad scanner, the structure sensor scanner.
Yes.
I always get that mixed up. But it's really came a long way.
It has, and if you look at the newer generation of the structure scanners, I mean, with every new version that has come up, the level of accuracy that you can obtain with the scan has significantly improved. So yes, in terms of portable scanning technology, I think that was the first big thing, moving away from the white light scanners that had to be plugged in. The key about using the structure scanners and with the iPad is about calibrating it, and and I think because it uses part of your iPad camera as well to be able to take that 3D scan. It's important that it's calibrated well, and sometimes if you're constantly traveling, you're taking the iPad off the bracket. It's important that you keep recalibrating it from time to time. I think that's something that I've seen a lot of practitioners struggle with. They get the iPad, they get the structure scanner, they set it up, they calibrate it, they take a great scan, they're very happy with it. 2 days later, I can't get a good scan out of this. They're frustrated. Well, it's important, depending on how much you use it and how frequently you move it, you may need to just recalibrate it. And even that has gotten better over the years. I have used the very first generation structure scanners as well, but being able to recalibrate it routinely in bright daylight made a difference. And when you use any of these scanning devices, I think it's important to have a proper setup. I think that's something we also need to talk about. How do you scan the underside of a foot? How do you scan the
environment?
The environment in which you're scanning is also important, which is where having that the app on your phone really makes it easier because you don't really need a whole lot of setup. It's much more easier and convenient. So I would say there's certainly a learning curve to scanning with the phones and the apps and the structure scanners. How far you need to be away. So watch some YouTube videos on how to take a good scan using a structure scanner. There's plenty of videos out there, and a lot of these apps have tutorials on. It definitely takes some practice.
It does,
yes.
And I think just because we're short for time, but you mentioned something that's so important, that the environment of the scan and of the room that you're scanning in plays a significant role when we're talking about these mobile applications, right. Whether it be the iPhone or using an iPad with the structure scanner. This is, because we're talking about affordable shape acquisition, you don't get some of the benefits that you would with some of the more expensive, the white light scanners and things like that, the blue light scanners, which, what I have done when introducing 3D technology to clinics and trying to find a consistent way to use these tools is to validate a single room where the light doesn't change, the environment with people walking back and forth doesn't change. You feel comfortable in that room. The patient feels comfortable in that room, so that when you're scanning an arm or a leg, you're not having to experience a whole bunch of different environments. And that is how you go from some repeatability challenges to validation with the mobile applications. But with the big scanners, they're big and they have lots of benefits. Lots of benefits. The accuracy is crazy.
Yes.
The ability to not have to do such validation through environments, that's pretty nice too. The full color scanning, now that the mobile applications can do that, that was something that the white light scanners and the blue light scanners had for a long time.
Right.
But
well, the thing with the white light scanners is, yes, the level of accuracy that you can get with a good white light scanner is very impressive. But you have to really look at the application. There are certain applications where you may need that level of accuracy, but you also have to think about, with a white light scanner, you have that flashing white light. Now, some patients may be very sensitive to, strobe lights effects and may not like that. So really, it's important to know your patient model. And see if that's the right application for it. Certainly I've used the white light scanners. We have multiple white light scanners at some of our clinics. For certain applications. The white light scanner works best, but for some applications it's easier to use the structure scanner or the phone app. Especially if you're seeing patients outside. If you have to go and see a patient at the hospital or nursing home to carry that entire white light scanner setup, it has to be connected to your laptop, and you have to do the whole setup, and it's time consuming, but it may be the right option for the right application.
Yeah, and we'll close on this. Something food for thought. Think about how much volumetric change someone with a residual limb goes through from the morning to the evening. And when you're looking to invest in a scanner just purely based on accuracy, you
how
could
much
scan
level of
in the
accuracy
morning.
do you want?
Yes, you could scan in the morning, but the reality is in the afternoon that limb is going to look how many millimeters different. So, just take that and think about with a mobile application of a 0.1 millimeter of tolerance there to a white light or a big cumbersome scanner, and I'd say cumbersome, but a highly accurate scanner of 0.01 millimeters, talking about a tenth of a millimeter here. So.
Yep. And the cost difference.
The cost.
How much does a typical white light scanner cost?
At least 10 grand.
Yes.
Well, I think the peel can be right below 10 grand, but anywhere from, it's thousands of dollars.
Correct.
Let's just
versus a structure scanner with an iPad setup could be, under 2K.
Yeah, definitely under 2K.
You know, and then when you go with app-based applications on your phone, you can just have a monthly subscription model, and there are multiple options available within those. So
yeah. So now that we've talked about scanning, which is clearly without a good scan, the rest of the workflow becomes more challenging, wouldn't you say?
Sure. Well, I do want to add though, if scanning is something that a practitioner is not comfortable, but still wants to embrace the digital workflow and 3D printing in general, it's okay for you to take a cast, and then you can then scan the cast, and then you can digitize it. So if you're a traveling clinician and you take 5 different casts at different places, and you bring it back to the lab, and then you have just one scanner in your lab, and then your technician can just scan all of those and digitize your casts. So that's important to note. Or you can send it to somebody like Spentees, or a central fabrication facility can take your cast and they can digitize your cast for you. So really, it's easier and convenient if you can scan yourself, but if you're not the person to scan, you want somebody else to digitize your cast for you, that is certainly an option.
Yeah, dip your toe in it and just get started.
Yeah.
Right.
Yeah.
After a scan is taken, there is rectification or corrections, modifications, whatever you call it, that needs to be done to that scan.
Correct.
The way that I best, talk about 3D scanning and rectification and things like that is the 3D scan is your just unmodified mold.
Correct.
If you think of like in a traditional sense.
Right.
It's completely just right out of the cast and it's unmodified. So you have to modify that scan and rectify it. And there's different tools and ways to do that. In our previous webinar, you were talking about how you use Mesh Mixer and you use maybe Omega. I mean, there's so many ways to clean up scans now.
Right.
But what is the best way that you have found to clean up scans, like for, we keep going back to check sockets, but I think that just having a case scenario of rectification can help the audience understand of what it looks like to do that. And I would also like to explain, after you finish that, of what you do for an AFO.
Sure. So, I mean, let's talk about, a below the knee residual limb to begin with. So, you take a scan, and, now you want to do your clinical modifications, which would entail, either reducing it volumetrically by a certain percentage or a certain ply, maybe removing some material or adding pressure to certain areas in the residual limb that are weight tolerant, or adding more material on that digital model in areas that are pressure sensitive. Maybe reducing the length a little bit depending on how much soft tissue there might be. Doing some compression. That is something that you can use different softwares to do. It's certainly possible with a free software like Mesh Mixer.
Sure.
Of course, there's a little bit of a learning curve with that, because Mesh Mixer is great. I love Mesh Mixer. I use it all the time, but it does have some limitation. It's not very O&P specific. But there are apps like there are applications like the Omega from Willowwood, or the Rapid Plaster from PVA Med, or the Spentees application that really are designed to be very O&P specific. So it's as easy as, if you want to do a 3% volumetric reduction, you just slide a bar and you get 3% volumetric reduction. Imagine doing that on a physical plaster model. I mean, you have to take 10 tape measurements, note it down, and then calculate on your and then write it down, and then scrape it, and keep measuring it till you reach that. I mean, you literally just slide a slider and you have a 3% reduction. If you don't like it, slide it back. You can't do that on a plaster model. Control Z is the the most favorite tool in the digital modification lab. I mean, so that is what the clinical modifications are about. We also have to talk about, now let's talk about an AFO. You take a scan and the patient is, maybe slightly plantarflexed, and you want to correct that. I mean, how do you do that in a cast? You have taken a cast, you look at the cast, oh, it looks like it's plantarflexed, and you want to dorsiflex it. Well, you cut the cast, and then you trim the cast, and then you staple the cast together, and then you look at it again, and then you cover it up, and then you fill it up. With an app like Spintease, you take a scan, oh, it's a little plantarflex. I mean, you slide a bar, and then you can just, it takes 2 seconds to do some of those corrections on the model itself using an app. And that's a big advantage of the digital workflow. The amount of time it takes to do the clinical modifications on a plaster model versus a digital model is significant. And then to be able to just undo what you did when it doesn't work, or you did something and you tried it on a patient and it didn't work, and you want to go back. I mean, imagine having to go back to the plaster model and then undo all of that and then do something else. I mean, it makes it so much faster, efficient, and convenient having a digital model.
Yeah.
Now, I will say this. There are certain patient cases where it does make most sense to actually take a cast and then digitize it. You cannot really, just scan everything that comes through the door. I mean, sometimes I have seen a patient with a below the knee amputation that has a lot of, redundant soft tissue. And, and I know that, when I take a hand cast, I can, position the cast,
Yep.
I can mold it in a way where, it will be in the shape that I want it to be. And in some of those cases, it might be best for me to take a cast and then just digitize that cast, because there's certain things that I can do with the hand casting that I cannot necessarily do with scanning. Although, I mean, there is a lot you can, but,
No, that's the reality.
Yes, and, sometimes you may be, trying to scan a kid with high tone, and you may not be able to, and that, you can get the correction better when you hand cast. You have more control over that. So, for some type of deformities and some type of, clinical conditions, sometimes it's best to take a cast and then just digitize your cast. So I think that's important to know, because I think a lot of people just argue that, if you're scanning, you should just scan everything. I can tell you from my experience, not everything is directly scannable. Sometimes it makes sense to take a cast and digitize, and that's okay. Whatever is best for your patient.
Yeah, the whole reason why any of O&P exists is to be focused on the patient.
Correct.
So, we could talk about efficiency and how things speed up, but if it's not best for the single patient in front of you,
right?
Why even think about it? Do what's best.
Right.
Now, after a scan is complete, the modifications, the rectification, whatever you call it, is complete. You then need to 3D design the orthosis or the prosthesis.
Correct.
There's multiple ways to go about this step. In fact, if you've done any investigation into 3D technology, this sometimes is what seems as what the bottleneck is.
Sure.
Because 3D design can be, it could be anything from fully automated using templates,
right,
to, semi-automated using some automation to help, maybe after you have
created some templates, maybe.
Some templates or scripts. Correct. Essentially.
Right.
To really full freedom control. You're starting from scratch every
right.
single time.
Right.
Some of the more popular softwares or design studios essentially is what they are, design software. In O&P today would start with Mesh Mixer. You can actually do more than just your modifications in Mesh Mixer. You can actually design the devices there.
Yes.
Which is starting from scratch.
Correct.
Can you create scripts in Mesh Mixer?
You can. There are ways to create some AI, to integrate some AI into Mesh Mixer, but you can also create some templates. So if you're designing a below the knee socket and you are always going to design it, or there are times you're going to need a a lock receptacle at the end of the socket, you can, that lock receptacle is going to be the same dimension no matter what type of socket you're making.
Always.
So if you make a template for a lock receptacle, and then you save it as a template. So after you're done modifying your model of your your BK or an AK model, you can just import that lock
component
template, and you can componentry essentially, and you can just attach it to your digital model. So yes, some level of automation, some level of AI and templating is possible with Mesh Mixer.
Yeah, and Mesh Mixer is a sculpting software. So there's technical specifications of these different types of softwares. You have sculpting, you have parametric design, and then you have the mixture of both, which is sculpting and parametric. But the parametric design software is more like a Fusion 360, where it's really built for engineering, and creating actual like engineered products, less like the I mean,
it's not
the
necessarily for organic.
Organic, there we go. Yeah, that's the word I'm looking for. Very organic, even like with some of the sculpting tools you get on Spenties.
Right.
So parametric works well, especially for the componentry, like you're saying. But I think up until this point, there's been a lot of segmentation with different software. Maybe you use the Fusion 360 for the componentry, then you use, or before that, you use Mesh Mixer for modification, then the different software for componentry, then the different software for the actual design of the device.
That's how it used to be a few years ago, because there weren't many platforms that had a one-stop solution, so to say, where you could do your scanning, your modifications or your rectifications, and then designing all in one. Today that's not the case. You can elaborate more on the options that we have today.
Well Spenties has, because we have seen the segmentation, indeed we wanted to create a one single place to do the scanning, the modeling, and the printing of the devices. We actually take a different approach to where we use templates for specific models, and then for other models you have the ability to start from scratch and really create something unique. And our model works well for the consistent daily use of 3D technology. But I want to be fully transparent. There's some devices that you cannot make on our workflow today. And that's where for us, we lean into, we have a design team as well that can help support for some of the very complex devices that can't be made on the application. And I think that model works very well, because you're still not having to learn some of the complex modeling that would be necessary, but you could still take advantage of the 3D technology for even the most complex of cases. But for folks that want to really take a deep dive into learning each and every aspect of 3D design, they're likely starting with watching maybe Limb and Lattice, some of the videos on YouTube.
Derek Smith has done a great job with a lot of videos and tips and tricks on using Mesh Mixer to do the designing of the sockets.
It's fantastic.
Very impressive. Yes.
It's a good way if you want to really get the basics of 3D design. And also,
and if it's something you want to put your time into, if you want to design it yourself, yes, certainly a resource for you too.
That's the way most folks get started. YouTube and leaning into their network if you want to design yourself. But then what is available today, like you're mentioning with Spenties and other people that are, here to create technology for ONP, is that a lot of that learning curve is mitigated with simple to use, streamlined
So with an app like Spenties, once you are done with your rectifications, you can take your model and you can just draw your trim lines where you want, and then the app will just design the device for you, and then you can customize it to, if you want to put a design or perforations or slots or holes or whatever, you can do all of those with just click, a few clicks, and it's very interactive. So you have a 3D model that you can, rotate around on your iPad or your phone, and or your computer, and you can see how the finished product will look before it's even fabricated.
Yeah, it's visualization. It's guided. Which is a big step if we want folks to be able to take advantage of 3D technology.
Sure.
Without a long learning curve, you do have to guide and use only specific tools available to the flow there.
Yeah. So, and there are other applications as well. The Mercurus has a software that allows that. Rapid Plaster has stuff for prosthetics that allow you to do that. So there are multiple different platforms that people can visit and choose from that helps them design the device.
Yeah. So kind of bringing all that together, and then let's jump into printing, but bringing it all together, you have really start from scratch, you have templates, and you have really a mix of both. Starting from scratch or templates. And
or if you don't want to do any of it, take a scan and just send it to somebody like Spenty's, or Bionic, and then we just do all of it for you.
So there's fantastic digital designers that are all over the world that are willing to do the design for you.
Right.
After design is complete, we now need to go into printing.
Correct.
I want to show the audience a really quick video from our partner from Xtol, who's going to share with us multi-jet fusion printing. This is the printing technology that is being used today for a lot of the definitive prostheses. We use it for AFOs and pediatric AFOs that are printed in nylon. But I asked Xtol to share with me this video so that you could take advantage of hearing it straight from the manufacturer. So here's Xtol.
HP Multi-Jet Fusion is a powder-based 3D printing process unlocking new efficiencies geared towards enabling production. Let's take a closer look at the printing process from start to finish. The process starts by evaluating each part and selecting the optimal print orientation. The parts are then placed in the build envelope. Special care is made to balance height and pack density while avoiding sudden changes in printed surface area. Parts are nested in 3D space within the print envelope, which is approximately 15 by 11 by 15 inches. Once the build is packed, it is sent to the printer. The build unit is inserted into the processing station to be filled with powder. The station automatically fills the build unit with the desired ratio of recycled and new material. Typically, the mixed ratio is 80% recycled and 20% new. The multi-jet fusion printing process uses the highest percentage of recycled material of any 3D printing process. Once filled, the build unit is inserted into the printer and the printing process is initiated. The parts are grown layer by layer, 80 microns at a time. There are 4 steps to the HP multi-jet fusion printing process. First, powder is spread across the build area. Next, fusing and detailing agents are jetted onto the powder. These aren't binders, rather they respond to IR energy. The fusing agent absorbs IR energy and causes the powder to get hot, while the detailing agent evaporates, causing the powder to cool. This causes a sharp temperature transition, which results in a fused part with distinct, precise edges. Multi-jet fusion parts are stronger than those printed with SLS and other technologies due to greater energy exposure. On each pass, energy is absorbed multiple layers deep, creating strength in every direction. Once the printing is complete, the build unit is removed and the cooling process begins. Builds can be naturally cooled or fast cooled in the processing station. A full build naturally cools in about 24 hours and then is ready for unpacking. First, the build unit is inserted into the processing station and the archaeological dig begins. Unfused powder is vacuumed away and reclaimed for future builds. Parts are extracted and excess powder is removed. The final step is media blasting to strip the remaining unfused powder. Depending on part size and geometry, this can be automated or done by hand. The parts get a final blow-off and are ready to be used for functional prototypes, tooling, or production applications.
So multi-jet fusion.
Yes.
It's impressive. You could print a lot of things at a single time, which is called batch printing. And you know, for us to be able to use that technology, or just over the last few years, has really advanced some of those strength capabilities that you're referring to.
Yep.
The quality, the surface quality, because of the reduction in layer lines is pretty big. Post-processing with vapor smoothing and dyeing black, and this is something that is being used on a daily basis today, because it just makes sense with the mechanical properties and the way that all of this is married together for the fabrication of devices like orthoses and prostheses and definitive use. You just get a great product. It doesn't work for every application.
Correct.
In fact, most printing on multi-jet fusion can take anywhere, if you have the printer in-house, can take, you know, a day, 2 days sometimes. To, you know, if you're outsourcing, it could take 5 plus days.
Yeah. Which is not very different from a traditional central fabrication facility. I mean, look at the quality of the print you can get with MGF printing.
It's incredible.
You know, in terms of weight, in terms of durability, in terms of, you know, just how thin and how lightweight you can get these devices made. The challenge with MGF is the time it takes to print. I think it's on average, you know, a batch would be 24 hours and maybe 24 to 48 hours of post-processing. Is that?
Yeah, I mean, it's variable. It could go, it could go much less or much faster.
Sure. But, you know, how many O&P practices can afford to have an MGF printer at their lab? So this is a great technology, and it's ideal for a lot of applications like this AFO that I'm holding. But you know, if you are hoping to use technology like this at your practice, an ideal starting point would be, you know, you take your scan, you do your rectifications, and you can use an app like Spenty's to help design. But then printing would probably make more sense if you outsource it to somebody like Spenty's, and there are other you know, places.
Yeah.
Ability Made is another option, and there are a few folks in our industry that, you know, do a lot of MGF printing. So it would make sense to you know, implement your digital workflow in a space where you are taking a scan, you're doing the modifications, you're helping design the brace, but then the fabrication of the brace itself is outsourced to a facility. And really the turnaround time, like you said, is, you know, 5-7 business days, maybe even 10 business days, which is not very atypical, you know, as compared to traditional, which is about the same time, but you get a much higher quality product that is very, very impressive.
Yeah, the testing has been done on multi-jet fusion, and it's going to be, I think it's going to be a critical technology in the future.
Absolutely.
But it's not for every application, because it takes, like you said, even just the lead time.
Sure.
You can't do same-day fittings, or,
sure,
you know, let's talk about FDM.
Yeah.
How does that work?
So FDM is, you know, another form of, you know, 3D printing. Essentially, it either takes filament or pellets, and then it melts those, and then it just lays it, you know, on a print bed layer after layer till, you know, the product is printed. There are FDM arguably is the most economical way of 3D printing today. as far as I know. And with FDM, the advantage is you can print pretty quickly, and the post-processing is, very limited in something like FDM. Now, again, it depends on the type of printer you have and the materials you're using. So, like we spoke about in the first webinar, my first socket that I printed on an FDM printer took about 70 hours to print. Today, my socket takes about, an hour and a half maybe to print. That's because, printers have improved so we use the Filament Innovations Icarus printer today. We have multiple of their high flow printers, uses a 2.5 millimeter nozzle. It's a high flow extruder. It oozes out a lot of melted plastic very, very fast, and it prints very, very fast. That's one of the examples here. So it can take, depending on the type of printer you have, it can take anywhere between 3 to 4 hours to from 1 hour to 3 hours to 8 hours to 10 hours, depending on the type of printer and material you're using, to print a socket, in-house. And depending on what you're printing with, I mean, if, whether you're using PETG or you're using copoly or other materials. Now, when you're talking about test sockets, transparency is something that's important. So if you look at 3D printed test sockets from a few years ago, you will see, because high flow wasn't really a thing. So when you printed using an FDM printer, the nozzles were so small that it had to create an outer layer and an inner layer, and it had to do the infills in between. And even when you're printing with a transparent filament with that, when the printer prints that way, just because of the way it prints, you lose the transparency. So the way the sockets used to be printed were, you would print it with holes in it. So because a traditional test socket is see-through, and that's the whole purpose, that you fit it on a patient and you can see through it, and you can visually see if it's loose or tight or too short or too long, and then you can modify it. Well, with the 3D printed test socket, that was hard because you lost transparency with it. So you would print it with some holes, so that kind of help you visually inspect the fit. But now with the high flow technology, I mean, you can print a socket that's really, really transparent. I mean, this is a 3D printed socket. So this because of the nozzle, the way it prints it, it doesn't have to do an outer and inner layer and an infill in between. It just, in one pass, it can do the layer, and because it's skipping all of those infills, you can have level of transparency. If you look at the level of transparency, so you can get it at as close as possible to your traditional test socket. And this is the same exact material that's used in the traditional material. It's PETG, it's just in filament form, and you get a test socket that you can put it on a patient, and you can travel with this. This one was printed on the PVA Med printer, and the quality, the level of transparency you can get with it is pretty impressive.
Yeah, I agree.
Yeah. And in terms of material science, things have improved, because now we have moved from just making test sockets to making flexible inners. I mean, you can use TPU and other materials to really make flexible inner sockets, to preparatory sockets using copoly. Again, these are materials that O&P professionals are already familiar with, to dare I say, definitive sockets using FDM technology as well. It's getting there.
The day is coming.
The day is coming.
Well, I hope you enjoyed this conversation about 3D technology and the ins and outs of the different aspects, from scanning to rectification to digital design to printing, and a very small piece of materials. I know you have plenty more questions, so please put them in the chat. We will answer these questions as they come in. There's what I urge you to do as well is to take your time to reach out to the different providers in the industry for the different materials and printers, and ask questions to them, learn from them. Ask me, ask Sagar and Bionic. We are here to help answer, and you'll find that the majority of people in the industry that are working on digital are here for you to answer these questions. So join us next week, as we talk more about the digital workflow. It's been a pleasure. So I'm Bryan with Spinties, and I'm joined by
Sagar from Bionic.
And we'll see you soon.